This is video 2 in our third rock from the sun, our geology unit. We're starting on slide 28. This is plate boundaries. We're still in chapter 14 in Miller. So plate boundaries, we're going to do a lot of activities on this, but we started to talk last time about the whole continental drift and plate tectonics theory. So now we're going to take a closer look at those plate boundaries. And again, you can see them really clearly in the map. You can see that the geology matches and makes it, just make a lot of sense. So there are 3 different types of plate boundaries. First type is a divergent boundary, and that's where the plates are moving away from each other. The convergent boundary is where the plates are moving toward each other. And then the transform boundary is where they're sliding past each other. So you have a couple different types of divergent. You have an oceanic divergent boundary, where both of the plates are underneath an ocean. So these are all the processes that would happen from a geological standpoint that would happen. You would get an extension. Think about it. If the plates are moving away, there's not going to be just random nothingness in the middle. Now you're going to create actually new Earth. So a divergent boundary creates new ocean floor where magma comes up and cools off as it hits the cold ocean and turns, cools off, hardens, turns into new ocean floor. So it usually creates a ridge. It's kind of like a thermal bulge where there's a lot of energy coming up and bubbling, and then that very thin lithosphere is right at the ridge. As it cools off and sinks, it's going to move away from the ridge and make more and more and more. So those mid-ocean ridges are very thin lithosphere, very hot right at the center, where that magma is coming up because the 2 plates are moving away from each other. You get this extrusion. The magma is basaltic, which is really, really dense. It is melting. And then you have a lot of very shallow, just under the surface earthquakes where those ridges are, because there's so much energy there and so much movement there. So we have proof that the age of the rocks as you move away from those ridges is getting older and older and older. So the ocean floor is actually the oldest, right along the edge of the continents. Okay, this shows that you see that mid-Atlantic ridge where you have stuff coming up. The North American plate is moving away to the left, the Eurasian plate, or west, sorry. The Eurasian plate is moving away to the right or east, and you have this magma coming up right along the mid-Atlantic ridge, and you see that here as well. Same concept from a different picture. Okay, so a continental boundary where you still have a divergent boundary, but this is where the continents are moving away from each other as opposed to oceanic. This is where you end up with hot spots, with plumes. The continents itself can kind of act like a blanket. They kind of elevate the temperature in the mantle and focus the activity in a specific spot as opposed to along a ridge. Those mantle plumes where you have that pocket coming right up is an important part of that. Underneath Tibesti, Africa is an example of that hot spot under a continent, and this is where you see that rifting pattern. So what that means is that you have 2 rift arms that open preferentially, that open based on what the magnetism of the Earth and all that kind of stuff is doing. It uses the current geology, the previous structures, and a thinning crust from all that heat and energy, and makes a graben. The crust sinks as the bulge dissipates. Eventually you get ocean coming into that rift, into that hole, and then it turns into an ocean basin. So you see that picture here. You have this hot spot right here, and hopefully this will make a whole lot more sense. We're looking right here along Africa, where you see the 2 plates moving apart. And you have this rift, this one hot spot as opposed to a nice long ridge coming up underneath, and then you see this is where the ocean would come in and fill in as everything cools off and kind of calms down. This also happened like the Baja Peninsula in California. You could make the argument that happened there. Okay, the next type is convergent boundary. The convergent boundary, the crust was destroyed. And it makes a mountain. So you have 3 different types: an ocean-to-ocean boundary, an ocean-to-continent boundary, or a continent-to-continent boundary. This is where you get a lot of the crazy stuff, the volcanoes, the earthquakes, all that kind of stuff going on. I'll let you read through this on your own, but this is where you get that really active stuff is where they're coming together, and you can imagine that would be a lot of energy pushing it against each other. The ocean to ocean convergent boundaries, that's where you get the really, really deep. The Marianas Trench, deepest part in the world, is at an ocean to ocean convergent boundary. Because what happens is you have subduction, which I should be, okay. So you get these deep ocean trenches. So the earthquakes are defined by that zones. You see what ends up happening is where, as they are moving together, these two oceanic plates, one of them, the more dense one, will subduct, will go underneath the other less dense one. So usually the continent is less dense and the oceanic is more dense. And this is where you get all the earthquakes. This is where you get all the volcanoes right off of this. We have all this crazy energy going on, and you see where those patterns are coming from. Okay. Again, this is a lot of detailed information about this. You can read through it on your own. Let me know if you have any questions on it. This is where we get volcanic island arcs, like the Hawaiian Islands, Aleutian Islands, Indonesian islands. All of those are formed from this movement. And you can see that right there. So you see this trench pushing down. Right at the edge of that trench, you have the hot spot. This would be the active volcano. These are older volcanoes that may not have as much energy. As the farther they move away, as the plates move, the less and less active they'll become until they become dormant and then sink into the ocean. Ocean to continent boundaries. Heat's added to the crust. It's a lot of, again, a lot of energy, a lot of movement. This is a lot of detail for you guys. I want you to get across that all of these boundaries are all subduction zones. One is going to have to go underneath the other. Make sure you can tell the difference. Get some examples of each type. And let me know if you have any questions. And we'll go into more detail about this in class. Transform boundaries are where they slide apart from each other. So you'll have like segments of the mid-ocean ridge, and they're moving past each other. There's a fracture zone where that's where that breakage is actually going to happen, and this is where you see a lot of earthquakes, because it's, as you can imagine, if they're grinding and pushing against each other, they tend to slip suddenly a little bit, and that is what causes an earthquake. You see the picture of the San Andreas Fault there. The Pacific Plate is sliding north relative to the North American Plate. These are connecting, transform boundaries are connecting other plate margins, other convergent and divergent. So kind of fixing and picking up the pieces of everything else. You see those diagrams there. Okay, hot spots, like we talked about already, is that hot material is just this one little spot, one little area where you get a plume of material, of magma, etc., that's pushing up. The source seems to come from that boundary area inside the mantle where the plates are either converging or diverging. And it's the hot spot is a fixed position, but it's underneath a moving lithospheric plate. And again, that's where you get those island chains, like the Hawaiian Islands. And we'll talk about that a little bit later. So you see where all those hot spots are moving. We can kind of map it and track it as time goes on. So like I said, the islands are associated with the hot spots. We can track how fast these plates are moving, because we can see how far the islands, the distance between the islands and the rate of movement of the Earth. Iceland, Galapagos Islands, Hawaiian Islands, you see that those linear island chains are all as the plate moves over the hot spots. And that's an example there. So you see the Hawaiian Islands as they're all coming out along there. You can see the time in between the Earth moving and the plate moving. Okay, so we want to assume that the plates are rigid. There's no internal change, bending or flexing or anything. That means that the plate motion has a rate and has a direction, which is awesome. We can measure that and map that. We can look at the magnetic strips, and we can look at the hotspot trails to figure that stuff out. And then your summary here, I just want to kind of pull everything together for you because there's a lot of detail that is not necessarily something that I want you to memorize. I just wanted you to kind of read through it so you understand it a little bit better. But what I do want you to know is what's on this chart here. So a divergent moves away from each other. That's the ridge. You end up with new ocean floor. The convergent is when it's moving toward each other. That's when you call the trench from subduction. And then the transform is sliding past each other. And I think, yes, that is where we stop. This is a short one.